1. ALGOL W. ALGOL W was intended to be the evolution of ALGOL 60, a language beloved by academics for its mathematical elegance. Imagine a language that promised to combine clarity, modularity, and practical features, all in one package. ALGOL W introduced record types, flexible arrays, exception handling, and even the early seeds of object-oriented concepts. On paper, it looked perfect. The language of the future. In practice, programmers quickly discovered that perfection can be dangerous. Compiler implementations were inconsistent, error messages were cryptic, and subtle syntax rules often led to hours of debugging with no visible progress. Meanwhile, COBOL had captured the business world, and Fortran had cemented its place in scientific computing. ALGOL W became the language that promised the moon, but left developers stranded on Earth. Despite its failure, ALGOL W left a legacy. Concepts like structured exception handling and data structuring influenced later languages like Pascal, Ada, and C. It also became a cautionary tale in programming history. A language can be elegant, technically brilliant, and still fail if timing, adoption, and tooling are ignored. Programmers who dabbled in ALGOL W remember the mixture of awe and frustration, beautiful syntax that rewarded precision, but unforgiving when mistakes were made. It was the intellectual equivalent of a luxury sports car that refuses to start unless you know exactly how to operate it. 2. PLI, or Programming Language 1, was IBM's ambitious attempt to unify business computing and scientific computing. It aimed to merge the worlds of COBOL and Fortran into one grand, do-everything language. PLI introduced multitasking, exception handling, complex data structures, and a host of advanced features. It sounded like a dream, especially for corporations tired of juggling multiple languages. The reality? A nightmare. PLI's syntax was bloated, compilers were slow and inconsistent, and debugging often required more skill than the programming itself. Companies had invested heavily in COBOL, and scientists relied on Fortran, making PLI adoption a logistical headache. It became a language admired in theory but rarely used in practice. Despite this, PLI did leave its mark. Concepts like structured exception handling and multitasking influenced later languages, proving that even failed languages can shape the evolution of programming. But for everyday programmers, PLI was the language you respected from afar, but never touched, like a museum exhibit you'd admire but never drive home. 3. Ada. Ada was the US Department of Defense's ambitious solution to programming reliability. It was designed for embedded and mission-critical systems, boasting type safety, modularity, and strict compile time checks. In theory, Ada was perfect. No unchecked errors, no ambiguous behaviors. It promised the perfectly safe software. The problem? Human programmers rarely appreciate perfection when it's rigid. Ada's syntax was verbose. Compilers were slow and development cycles expensive. By the time Ada matured, C and C++ had already captured the mainstream developer base. Ada became the language of government contracts and high security projects, but never mainstream. Despite its failure, Ada taught valuable lessons. Concepts like strong typing, exception handling, and modularity inspired modern programming languages. Ada survives in legacy systems, quietly running embedded defense and aerospace applications. It became the language for people who like to suffer elegantly, admired for its rigor, but feared for its complexity. 4. INTERCAL. INTERCAL wasn't designed to succeed. It was a parody, created to mock the growing complexity of contemporary programming languages. Its syntax required politeness. Commands like please do were mandatory, or the compiler would complain. Loops, conditionals, and variables were intentionally obscure. It was confusing, obtuse, and utterly impractical, and yet INTERCAL thrived in one domain: cult humor. Programmers who experienced it could laugh at its absurdity and appreciate the commentary on language design. INTERCAL demonstrated that programmers value usability. A language that requires etiquette to compile is fun for a joke, but nobody will build serious software with it. Its legacy is purely cultural, a reminder that programming languages can be entertaining while still teaching subtle truths. Simplicity, clarity, and practicality matter. INTERCAL is a historical curiosity, the ultimate anti-language that left programmers equal parts amused and frustrated. 5. BCPL. BCPL, or Basic Combined Programming Language, was a precursor to the legendary C, designed for compiler writing and system-level programming. It introduced many concepts that shaped the future. Its syntax was terse, concise, and sometimes cryptic, which made it efficient but not beginner-friendly. BCPL failed to gain widespread adoption because it lacked general-purpose appeal. Developers appreciated it for experimentation and compiler development, but everyday software tasks demanded demanded languages that were easier to learn and more supported. The emergence of B and later C overshadowed BCPL entirely, yet BCPL's influence is undeniable. Modern C, C++, and even aspects of Java trace ideas back to it. BCPL serves as a reminder that failure and popularity doesn't erase a language's contribution to programming evolution. It's like a stepping stone in a river, essential for crossing but easily overlooked once you've moved forward. 6. Modula 2. Modula 2 was Nicolaus Wirth's ambitious follow-up to Pascal, designed to fix some of Pascal's shortcomings while introducing a robust module system. Imagine Pascal wearing a business suit, same intelligence, but suddenly ready for the corporate world. Modules in Modula 2 allowed programmers to organize code logically and encapsulate functionality, making it easier to maintain large programs. This was revolutionary at the time, especially in educational settings where software engineering principles were just starting to be formalized. The language emphasized safety and clarity. Type checking was strict, procedures were well defined, and it encouraged developers to think about design before diving into code. Sound familiar? Many modern languages like Java, C, and Python borrowed these principles, especially around modular programming and encapsulation. Modula 2 was, in many ways, ahead of its time. So why did it fail? Timing and ecosystem issues. By the late 1970s and early 1980s, C had already become the go-to language for systems programming, and Fortran remained dominant in scientific computing. Modula 2 had brilliant concepts, but lacked commercial libraries, tooling, and hardware support. Developers wanted practical solutions that could run across platforms and integrate with existing code bases. Modula 2 was too academic, too clean, and too isolated. It did find a niche among hobbyists and educators, and some organizations used it for embedded systems, but widespread adoption never came. Ironically, its influence quietly shaped later languages, Ada's modular concepts, Pascal extensions, and even aspects of modern software design echo Modula 2's design philosophy. For the programmers who dabbled in it, Modula 2 was a lesson in elegance, foresight, and how even a perfectly designed language can fail if the world isn't ready for it. 7. Lisp Variants. Lisp Variants were the gold standard for artificial intelligence research in the 1960s and 1970s. InterLisp and MacLisp brought features like garbage collection, symbolic computation, and powerful list manipulation, making them the go-to languages for AI labs. Researchers could prototype complex algorithms rapidly, and Lisp's flexibility allowed for experimentation that other languages couldn't match. But Lisp had a problem: usability. Its parentheses, heavy syntax intimidated newcomers, earning jokes like lots of irritating superfluous parentheses. Debugging long nested expressions was an exercise in patience and eye strain. Developers outside academia often avoided Lisp because it lacked standard libraries, commercial support, and a cohesive developer community. Despite limited adoption, Lisp left an enormous legacy. Concepts such as recursion, garbage collection, and functional programming influenced Clojure, Scheme, Python, and even JavaScript. Lisp was also one of the first languages to emphasize treating functions as first-class objects, a concept that defines modern functional programming. For developers who used it, Lisp was simultaneously a delight and a headache. It was elegant, powerful, and capable of tasks that would stump other languages, yet everyday practical programming, building business software or games, was cumbersome. Its failure in mainstream adoption highlights that raw power and academic respect don't always translate into widespread use. Lisp is a testament to the idea that language success depends not just on capability, but accessibility, tooling, and community adoption. 8. APL. APL was a mathematician's dream and a programmer's nightmare. Using unique symbols instead of letters, APL allowed developers to write extremely concise code for complex mathematical operations. A single line could perform matrix multiplication, statistical calculations, and data transformations that would take dozens of lines in conventional languages. However, this conciseness came at a steep cost. Typing and reading APL was challenging. Specialized keyboards were often required. For most programmers, maintaining APL code was like deciphering ancient hieroglyphs. It was impossible for large teams to collaborate efficiently, which hindered its adoption outside specialized environments. APL's niche was scientific research, finance, and high-level mathematics. Hedge funds in the 1970s and 1980s occasionally adopted APL for rapid modeling and calculation, because its symbolic power allowed allowed sophisticated algorithms to be expressed with minimal code. Despite this, it never achieved mainstream popularity. Interestingly, APL influenced modern array programming and inspired languages like J and K, which retained the focus on concise, vectorized operations. For programmers who mastered it, APL was almost magical, incredibly powerful, and frustratingly obtuse. It teaches an important lesson: power without readability or maintainability limits adoption. Even the most elegant solutions will fail if they are inaccessible to the broader developer community. 9. Smalltalk Variants. Smalltalk was revolutionary. Developed at Xerox PARC, it pioneered object-oriented programming, graphical user interfaces, integrated development environments, and dynamic runtime features. Using Smalltalk, developers could click, drag, and inspect objects visually, a precursor to modern IDEs and UI-based development tools. Yet Smalltalk failed commercially. The hardware of the time was expensive, limiting adoption. Corporations were wary of adopting a system that required cutting-edge machines and unconventional thinking. Meanwhile, languages like C were entrenched, with vast developer communities, libraries, and support. Smalltalk was too advanced for its own good, conceptually brilliant, but impractical for the broader market. Despite this, Smalltalk's ideas shaped the future. Java, Python, Ruby, and Objective-C all inherited object-oriented concepts pioneered in Smalltalk. Its IDE philosophy influenced modern development environments. Smalltalk remains loved by enthusiasts and historians as a beautiful experiment that demonstrated the future of programming, even if the world wasn't ready to embrace it fully. 10. Eiffel. Eiffel, created by Bertrand Meyer, aimed to make software reliable through design by contract, a system where preconditions, postconditions, and invariants were explicitly defined. This approach promised error-free software, theoretically ensuring correctness in every program. In practice, Eiffel was too verbose and rigid. Writing contracts for every function added significant development overhead. Tooling was limited, and mainstream adoption never took off. Developers appreciated the safety and clarity, but the language didn't integrate well with popular platforms or libraries. By the time Eiffel stabilized, languages like Java and C were gaining traction with more practical approaches to reliability and object-oriented programming. Despite commercial failure, Eiffel influenced the development of modern programming practices. Concepts like strong typing, formal verification, and defensive programming continue in contemporary languages. Eiffel is a story of perfection versus practicality. Brilliant ideas, but impractical execution for the broader programming world. It reminds developers that elegance and rigor are not enough. Adoption, usability, and ecosystem matter just as much. These failed programming languages show that brilliance doesn't guarantee success. Timing, usability, community support, and tooling all matter. Some languages faded quietly, leaving ideas behind. Others became cult curiosities, more admired for theory than practice. They are ghosts of programming history, whispering lessons. Innovation must balance practicality, and elegance without usability is doomed to obscurity.